along. So let's get into surface chemistry and heterogeneous catalysis. Okay, so this is into the subject, into the chemistry that I do. I consider myself to be a surface chemist. Amongst many things, we all wear very different hats. Sometimes we call ourselves this kind of chemist. Sometimes we say we're that kind of chemist. So I do atmospheric physical chemistry, as you all know. But deep down, surface chemistry is what's really interesting to me. Okay, so let's talk about the step Terrace Kink model of a surface. Okay, so this would be a molecular view of an interface. Okay, so of a solid, right? The top, let's say, layers of a solid. There are going to be defects, these surface defects. We call them steps in the case where there's, one plane and then another plane. That would be a step. The terrace is what's on top. Okay, so the flat part where you have atomically smooth. So when you see a flat line right here, that means it's atomically smooth. So there might be atoms there is atoms all along here, right? But there's some type of defect in the lattice that gives you that step. If we were to view from the other dimension, these steps, these corners right here, that makes what we call a kink. Okay, so very creative names here. And so what I'll say is when we're doing this heterogeneous catalysis, and this could be gas interacting with a solid or a liquid interacting with a solid, right? We can put, let's say, a platinum solid in a liquid mixture, and that platinum solid will function as a catalyst, much like this. Okay, so typically an atom or a molecule will not have much interaction with a terrace. It's atomically smooth. These defects, or these, I should say, lack of defects, usually render it inert. However, these steps and kinks are great places to stick what we call an add atom. So an atom that has adsorbed. So add equals, adsorbed. Not absorbed. It's tempting, I did it again. I can't talk and write at the same time. It's tempting to use the word absorbed like a sponge absorbs water, but we use absorb for photophysics, like absorbance in spectroscopy. So adsorbed means a molecule has stuck to the surface. Okay? Molecules typically have great affinity for steps and kinks, as I said, but it's certainly not uncommon to find them stuck to terraces. Okay? So often catalysts that have been roughened, that are not atomically smooth, work really well because those things that have those rough defects are great places to bind add atoms. Okay? So let's see here. Moving along. So there's two kinds of ways that atoms can become stuck. That's through chemisorption, which is chemical adsorption, or physisorption, which is physical adsorption. Look, I wrote adsorption. It's still even hard for me to get this straight. Physical adsorption. So chemiabsorption, as you might guess, involves the creation of new bonds at the interface. So new bonds. Okay? Physisorption is typically through a van der Waals interaction, right? So in physisorption, right, the molecules might be stuck, but they can certainly become unstuck. Chemiabsorption, that's very difficult, and typically chemiabsorption is irreversible. Okay, so there's been a new bond created that's binding that add atom to the surface of that heterogeneous catalyst. And because there's the creation of this new bond, it can be very difficult to reverse that and desorb the atom. And that's observed in the delta H of adsorption, so the enthalpy of adsorption. That's typically a dead giveaway when something has been chemisorbed versus physisorbed. So you can see here just a few examples of the adsorbent substrate, so the surface, okay, and the adsorbate, so like a chromium surface or an iron surface or a nickel surface. And if we look at these enthalpies, they're quite large when you look at the enthalpies of physisorption. And also, typically in these enthalpies of physisorption, the substrate or the surface isn't as important. And you notice here there's no indication of what the substrate is. The substrate's very important for chemisorption because of the creation of these new chemical bonds, right? So, to me, interesting stuff is what happens in this debate, or this, trying to determine if something has been physisorbed versus chemisorbed. And certainly for people who are in the business of molecular engineering, so people who are interested in creating new molecules for materials, so you might be purposefully trying to chemisorb something. What I study in atmospheric chemistry in the natural world is just trying to work out, has something been chemisorbed or has something been physisorbed? Naturally, right? Because that makes a big difference in the environment. If a small gas phase molecule chemisorbs to a surface, it's now probably become a permanent part of that surface. But if something has become physisorbed in the natural environment, that means it might bind to a surface and then later on desorbed, okay? So to me, in atmospheric environmental chemistry, it becomes very interesting working out these differences, okay?